For Chapter 3, Notes D, we're going to look at what happens when some of the elements in the third period bond with oxygen. So we're going to go across from sodium all the way to chlorine. Not argon, of course, because argon doesn't bond, but we're going to get up close and personal with a few of these elements and see what happens when they react with oxygen. So these are some of our oxides. Notice on the left side of the periodic table, the metals with oxygen, there's only one compound. And that's because there's only one way to balance the charges. These are ionic compounds. So for example, magnesium and oxygen both have balanced charges, +2, -2, so no subscripts are needed. Whereas sodium with a +1 charge, we would need 2 sodiums to balance the oxygen. And for aluminum, you would need 2 aluminums and 3 oxygens in order to balance the charges of +3 and -2. With silicon dioxide, we have actually a macromolecule. So that'll be the one set, that one ratio that it comes in. And then for our nonmetals, we actually have several different options, different stabilities of bonds that we're going to look at. So the first thing that you'll see in the notes is a big table. This table looks a little intimidating, but it's actually a really useful way to organize information and pick up on patterns. We're going to fill it in a little bit at a time. So we're going to start with some of the things we've already talked about, such as melting point trend. So let's focus on the melting point first, or the change from solid to liquid. So as you go across from sodium to magnesium, you have more electrons being involved in the transfer, and you're going to see more stability coming with that. So we see an increase in the melting point. Then as you move across to the P block, there is a small drop, and it continues to drop. But there is a big point at which there is a huge drop, and this is something you really want to note. It is right after the silicon dioxide, right after the macromolecule. This should sound kind of familiar from when we talked about the melting points of the pure metals. It's a similar trend, just excluding the small drop as you go from S to P. When you start talking about bonding, that is going to play a role, whereas it didn't with the metals only. Still, the most important thing to know is that you have this big drop as you go from the silicon dioxide into the pure simple covalent bonds. Then once you get into the simple covalent bonds, you're going to see a continuous drop. This is because the atoms, and therefore the molecules, are getting smaller. Therefore, there's less and less delocalization, movement of electrons, no real big difference in charges to keep the atoms together, the molecules together. So you're going to get less stability with the smaller atoms. So all the way furthest to the right, you're going to have the most insecure, unstable atoms, molecules, and so you're going to get your lowest melting point, the least amount of energy to break that up. So notice the phases kind of follow with that. It says that we're looking at room temperature, which they state is 25 degrees Celsius. So right around there, I mean, I know this says 24, but right around there is where we're changing from solid into more of a liquid phase. They say 25 degrees Celsius. Some other places I've seen publications state 22 degrees Celsius is typically where things are measured at room temperature. I do know 25 degrees Celsius is your standard temperature for thermodynamics. So I believe that's why they're using that as the kind of base point. But don't worry about a degree. Just know that right around here, right around that 24, 25 degrees Celsius is where we go from the solid phase into more of a liquid and gas phase. So speaking of gases, let's look at the trend in boiling point. Since the boiling point is the change from a liquid to a gas, you are going to see that at a much higher temperature, but the trend will be the same. You're going to see an increase as you go from the sodium to the magnesium oxides. Then you see a little bit of a drop as you get into the p orbitals, but you see a very big drop as you leave the network covalent compounds and go into the simple covalent compounds. So you see that big drop again, and then a decrease across the nonmetals. Same exact trends for the same exact reasons. So notice that some of our smallest compounds can even be gases at room temperature. Next, we'll look at conductivity. How good of an electrolyte these compounds are. How good they are at conducting electricity when they are dissolved in water. In order to conduct electricity, you need ions. things with positive and negative charges, in order to repel and attract the electrons through the water. So something that's going to be a very good electrolyte would need to have an ionic bond. Ionic bonds dissociate in water. So that's going to be our first three compounds: the sodium, magnesium, and aluminum oxides. Those are going to be our good conductors. Those ions, those salts, will dissociate in water. All of our covalent compounds will be non-electrolytes. They will not conduct electricity in water. And that is because they aren't going to break up into ions. There aren't ions composing those molecules. One kind of weird exception is our network compound, our silicon dioxide, which will somewhat conduct. Not great, but will somewhat conduct electricity. So we say it's a poor electrolyte, but it is notably not a non-electrolyte. The thing is, those electrons are spread out into a network, into this crystal structure that can, in a way, facilitate the movement of electrons as they move through the network. So it's not the same as having ions in solution by any means, but it is not a non-electrolyte per se. So since we're talking about the structure, let's go ahead and fill that part in too. We said that these first three elements were good electrolytes because they would break up into ions, so they're going to have an ionic structure. Whereas all of these nonmetals were non-electrolytes because they were covalent. So the difference we're making here, in order for silicon dioxide to be a poor electrolyte, talking about its network structure, those are very big molecules. So macro means big. Like macro observations you can see with your eyes. Microscopic observations you cannot. You have to make inferences. So we call them macromolecules. I always call them network structures, same thing. As opposed to just the regular covalent bonds that you've learned about in honors chem, we just call those simple covalent bonds. So we're covalent on the right side of the periodic table, including that network structure. But it is a bigger network structure, causing it to be able to somewhat conduct electricity. This is a really good example of structure to function. Because it's ionic, it's a good electrolyte. Because it's covalent, it's a non-electrolyte. Because that covalent bond is such a big molecule with lots of crystal structure, it can kind of conduct. So you have kind of three different categories here, where the structure dictates how well the electrolyte will be, or how good of an electrolyte it will be. So on the left side of the periodic table, we're going to look at the oxides of sodium, magnesium, and aluminum. Those metals with oxygen would always form ionic bonds, metal and a nonmetal, which means it's going to have a very large difference in electronegativity. You may recall the number 2, a difference of electronegativity of 2 is kind of the cutoff for ionic bonds. So we're going to have an electronegativity difference greater than 2 between sodium, magnesium, and aluminum versus the oxygen. So when it's an ionic compound, it's going to have a pretty high melting point. It's also going to be really good at conducting because when we dissolve it in water, we will get lots of ions. The metalloids are considered the middle of the periodic table. So for period 3, that would be our silicon. So our silicon dioxide is the macromolecule of period 3. Again, macro meaning big. So you can see how big and wide these networks go. And this is why they can be kind of okay at conducting electricity, because there's places for these electrons to move around. They also have a lot of stability associated with these networks because they're this crystal structure that's very set, and so that's going to dictate the high boiling points. That's why after this, we're going to see a big drop. So on this graph, you can see the big drop. As we go from the silicon oxides to the phosphorus oxides, the melting and boiling points go way down. So there must be a very different structure to these molecules. So when we're looking at phosphorus, sulfur, and chlorine, these are covalent compounds that are just going to be very simple. They're just going to come in single, double, triple bonds, just set numbers of elements, just very simple molecule. With these covalent bonds, you're going to have a smaller difference in electronegativity, less than 2. And so when you have less difference in electronegativity, that bond is more weak. And so you're going to get lower melting and boiling points. They're also going to be incapable of conducting electricity because they don't break up into ions in water. Let's get into some of the reactions you need to know for the IB test. So the first set is dealing with the more electropositive elements. If you think about electronegativity, it increases from left to right. So the ones on the left would be the least electronegative, or another way of saying that would be the most electropositive. So basically that means we're looking at the sodium and the magnesium. So these are the oxides for sodium and magnesium as they react with water. And again, you're going to be forming hydroxide solutions. So just like where the alkali metal would form an alkali solution with water, you're also going to see this sodium oxide form sodium hydroxide with water. It's going to have different coefficients because it's a little different to balance. As far as phases go, typically the hydroxides are aqueous. There is one exception where magnesium hydroxide is solid. It's actually the only hydroxide that's typically solid at room temperature. But if you were trying to apply this to other hydroxides, I would go with aqueous. So you do need to know these equations. I like to think of it as the S block elements as oxides reacting with water form those metal hydroxides. Although your S block metals are very basic, the aluminum is not so picky. Aluminum is something we call amphoteric, which means it can act as an acid or as a base. So there are actually two reactions you need to know for the aluminum oxide. One where it acts as the base, reacting with hydrochloric acid, and one where the aluminum oxide is acting as the acid, reacting with sodium hydroxide. When the aluminum oxide is acting as a base, reacting with the hydrochloric acid, it actually forms a neutral product, aluminum chloride and water. Whereas when it's acting as the acid with the sodium hydroxide, it actually stays basic as the product too, forming a very complex ion. This fancy molecule is known as sodium aluminate. Moving on to silicon dioxide, our network compound. Now, this compound is not really amphoteric, but it's not going to really be a strong acid either. It is, however, a weak acid, meaning it will only react with a strong base. Think about silicon dioxide as sand. Silicon dioxide is sand. It can be turned into glass, different things like that. But picture going to the beach. If silicon dioxide was reacting with a weak base, like water could be a weak acid or a weak base, then the water and the sand would be reacting under our feet. That does not sound very comfortable. Not to mention what sand would be left. The beach would just disappear. That would be so sad. So we only are going to look at silicon dioxide reactions as a weak acid, meaning they have to react with a strong base. So this is the reaction where silicon dioxide reacts with a very common strong base, sodium hydroxide. The products will include water and then something called sodium silicate, which is this compound right here, sodium, silicon, and oxygen. And again, I really want to emphasize that that reaction only worked because the sodium hydroxide is a strong base. If the silicon dioxide wanted to react with a weak base like water, it wouldn't work. There would be no reaction. Next, we're just going to look at the most common oxides for phosphorus, sulfur, and chlorine. Our nonmetals, our simple covalent compounds, as they react with water. These can react with water because these are going to be all strongly acidic. So we are going to be forming sulfurous acid. Notice the SO3, not SO4, coming from the SO2. Then we're going to form phosphoric acid. So PO4 is correct for phosphate, so it's just phosphoric acid coming from P4O10. And then we're going to form perchloric acid. So chlorate with ClO3, this is one more, hence the per for perchloric acid, coming from Cl2O7. I don't have any great memory tricks for these three set of reactions, so just stick with the flashcards. You do need to know these reactions. You should also know the relative acidity of the products. So you might recognize the perchloric acid as one of our 6 strong acids. And then as you go left from there, the phosphoric acid would be a little weaker, and then the weakest of the 3 would be the sulfurous acid. So let's go back over what makes something strong, or what makes an acid or base a strong acid or base, I should say. First of all, there's a list of 6 strong acids. These 6 acids are strong. Any other acid is not going to 100% dissociate. Only these 6. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. Only these 6 acids will 100% dissociate. There are a lot of things that depend on this dissociation, so I would recommend memorizing this list. So those 6 strong acids are going to be the only ones that dissociate 100%. But there are varying degrees from there. For example, we called the phosphoric acid relatively strong, and that's because it dissociates 92%, very close to 100%. And the less percent it dissociates, the more weak the acid would be. That dissociation is talking about how many ions come from the breaking of that ionic bond in the acid. The more ions in solution, the better of an electrolyte it will be, and the more reactive it will be in general. This is why we typically say the strong acids are more dangerous. So this table may help give you an idea of the patterns between what makes something a strong acid or a strong base, where those oxides are on the periodic table. So notice your strong acids are in the top right corner of the periodic table, where the strong bases would be in the bottom left corner of the periodic table. And then you have kind of a gradient of the weaker acids and bases towards the middle of that trend. So it's an interesting pattern to kind of help. It definitely shows how the chemical properties of elements can then dictate the types of bonds and types of reactions that they participate in. So let's take what we just talked about with the reactions of these oxides and finish up our big table. First, let's look at the reactions with the S-block metals as oxides. They will form metal hydroxides, very basic solutions. Then we had the aluminum oxide, which we determined was amphoteric. We looked at a reaction where it acted as an acid and one where it reacted as a base. But in both of these cases, it was having to react with a strong acid or strong base. The reactions involved hydrochloric acid and sodium hydroxide, both of which are very strong acids or bases. So when it reacts with water, which would be a weak acid or base, you do not see a reaction whatsoever. So we didn't talk about a reaction with aluminum oxide and water. There wouldn't be one. Similarly, there wouldn't be a reaction with the silicon dioxide and water. We talked about how it was a weak acid. So it is weakly acidic, but it will not react with a weak base. It must react with a strong base. So when we looked at that reaction, we were looking at it react with the sodium hydroxide only. And finally, we're going to look at the non-metal oxides forming some polyatomic products and increasing in strength as you go from left to right, with the perchloric acid at the end being the strongest acid. I do want to point out one thing that's a little inconsistent with the way this is presented because it may come off as a little confusing. In the notes, we've focused on SO2, but here, just to create a pattern that's uniform, they're using SO3. But IB does like to ask specifically about SO2 when they ask you to give them the reaction. But then as a pattern, understanding that the strength increases as you go from left to right is also something you should know. So kind of 2 different important things there. So here is the entire table completed. This is a good place to pause if you missed anything you need to fill in. I just want to focus on a few different things that you may want to make sure you have kind of highlighted. So the first would be the dip in the melting and boiling points as you go from your network compounds to your simple covalent compounds. So you see the big drop as you go from silicon dioxide over to your phosphorus oxides. And then you also see right around this 25-24 degrees Celsius, the change in phases. You should know how structure relates to function when you're talking about the electronegativity, electrical conductivity. How good the atoms are at conducting electricity depends on whether they're actually atoms or ions. So our electrolytes will be things that don't dissociate into ions, whereas our good electrolytes will dissociate into ions. And then understand that the large nature of the molecules is why you have something a little bit different for your silicon dioxide. And then, of course, the most important thing that took up most of these notes is the reactions. So whether something is forming a basic product like our sodium hydroxide or magnesium hydroxide, or whether it's acting acidic, forming some acid products, whether it's able to act as both an acid or a base, being amphoteric. These are very specific details that IB will ask about. And again, I recommend flashcards for the reactions because you do need to know all of these reactions and the reactions from notes C.